All right, everybody, let's dive in with lesson 3, derivatives of logarithmic functions. So we're going to be using implicit differentiation to prove that if y is equal to ln of x, the natural logarithm of x, then dy dx is 1 over x. A very, very important piece of information. So I'm going to start by just rewriting out the question over here so that everything flows nice and fluidly through my proof. So I start with y is equal to the natural log of x. I'm going to rewrite this, though, in its log form, its normal log form. So remember, the natural log is just the log based e. So natural log of x is log base e of x. And if I rewrite this in its exponential form, that means e to the power of y is equal to x. All right. Now, if I want to take the derivative of both sides, so d dx of e to the power of y is equal to d dx of x. Oh, hey, one of those is a real easy derivative. So the derivative of e to the power of y. Now we remember the derivative of e to the power of anything is just e to the power of that same thing times the derivative of that exponent. Chain rule, right? So this is e to the power of y times dy dx. So it's just e to the power of y times the derivative of y. And we know d dx of x is just 1. That's a convenient one. Which gives us that dy dx, if we just rearrange for dy dx, we get that dy dx is equal to 1 over e to the y. But here's the thing. Take a look. E to the y, e to the y, e to the power of y. E to the power of y is equal to x. We know that. So since e to the power of y is equal to x, I can actually rewrite this as dy dx is equal to 1 over x. Beautiful! Since e to the power of y is equal to x. Proven! We did it. Done. Not so bad, right? That one's actually pretty quick. All right, now that we know that, let's take a look at something we can do with that. Let's look at y is equal to the natural log of x cubed plus 3. So we want to differentiate that. So notice that we've only found what the derivative of the natural log of x is, right? But let's be real, we've done this 1,000 times. If we know what the derivative of something with x is, then to figure out the derivative of something where it's a function of x, we do the exact same process. We just have to do chain rule. We have to take the derivative of the interior function. So we're going to do the same thing here. So let's let u equal x cubed plus 1. And if we do that, that means du dx is equal to 3x squared. So what we get then is y is equal to the natural log of u, meaning dy dx is equal to 1 over u, because we know the natural log of something is 1 over that thing. But we have to multiply by the derivative of the interior function, du dx. Chain rule, right? So that's our chain rule. Cannot forget chain rule. Chain rule. There we go. Then we finish this thing up by substituting that u and du dx back into the equation. So this becomes 1 over x cubed plus 1 times 3x squared. Or, if we prefer, we can write this as dy dx is equal to 3x squared all over x cubed plus 1. It's just chain rule. It's a little new piece of information, that natural log of x derivative, and chain rule, and we're all done. Perfect. So in general, this is just a summary of everything we kind of already know. So we covered this. D dx of ln x is 1 over x, and hey, this is that chain rule version. Fun fact, these two are exactly the same thing. In one, it uses g of x to denote our function. In the other one, it uses u. It doesn't matter. They're the same thing, right? We could easily rewrite this as 1 over g of x times g prime of x. It's the same thing. No difference, right? So those two are just saying the exact same thing. They're just the chain rule of natural logarithm of x. And then we have this one, the derivative of log based a of x is just 1 over x natural log of a. This comes from some earlier pieces we did in previous lessons. And d dx of log base a of u, same idea, the exact same derivative, except it's chain rule version. So each of these is just the derivative and then the chain rule version of that derivative. All right, let's do some examples. So we're going to prove some stuff. Let's prove some things. Okay, so if y is equal to 1 over x times the natural log of x, then dy dx is 1 minus natural log of x all over x squared. So this thing is clearly going to bust out some product rules, so we should record our f's and our g's here. 1 over x, f prime is negative 1 over x squared. I did that one really quickly in my head, but just remember 1 over x is the same thing as x to the negative 1. If you're not sure about it, try it yourself. And we have g as the natural log of x, and we know from our previous result that g prime must then be 1 over x. Okay, so this means that dy dx is equal to our f prime times our g plus our, I didn't write a plus our f times our g prime, which gives us natural log of x over x squared, I should say negative natural log of x over x squared, plus 1 over x squared. Oh, hey, that's a delightfully convenient common denominator right there. Love that. So if I just rearrange that there, this becomes 1 minus natural log of x all over x squared. Boom, proven, done. We did it. Good for us. Hooray! All right, let's take a look at another one. Y is equal to the natural log of x to the power of 4. Okay, so we've got some chain rule going on here. So dy dx is going to be, we bring down the exponent, 4 out front. Natural log of x on the inside to the power of 3, so that's just power rule, times the derivative of the interior function. Well, the derivative of natural log of x is 1 over x. That's our chain rule. So what we're left with is 4 natural log of x cubed all over x. Proven. Done. All right, one more. So in this one, we have y is equal to the natural log of x plus 1 all over the square root of x minus 2. Okay, so for this one, there's a lot going on. Let's just deal with the inside right now. So let's set let u equal x plus 1 over the square root of x minus 2, meaning we're going to need to know our du dx. And in order to solve that, we're going to need quotient rule. So let's establish our f prime, g prime. So f is going to be x plus 1, meaning f prime is just 1. G will be x minus 2 to the 1/2. G prime then is 1/2 x minus 2 to the negative 1/2. Okay, so for our du dx, what we get is we're going to have f prime times g minus f times g prime all over g squared. Okay, so what we got now is we're going to want to simplify some of this. So first thing I'm going to do is just simplify the numerator and denominator a little bit. Nothing drastic. Just going to rearrange this a little bit. And most importantly, in the denominator, x minus 2 to the 1/2 squared. Well, basic exponent laws, we multiply our exponents. 1/2 times 2 is just 1, so this becomes just x minus 2. I can't write x's today. X minus 2. There we go. Okie dokie. Now, here's the thing. With something like this, if we want to simplify this as much as we can, I'm going to want to do some factoring. Now, I know how much you all love, just love factoring with rational exponents. So that's what we're going to do now, because I know that you adore that. So take a look at these two. They look almost like they're the same, and so that's why we want to factor from those. So what's going to take care of this? I'm going to actually pull out an x minus 2 to the negative 1/2. Now, if you're bad at this, if you're really bad at seeing it, watch what happens when I factor it out. So what I'm left with is x minus 2 to the power of 1 minus 1/2 x plus 1. Now, if you're like, I'm really bad at seeing that, just work backwards. Take a look at this. You'll know you did it right if you multiply it back in and you get the previous step. So x minus 2 to the negative 1/2 times x minus 2 to the power of 1, basically. Well, when we multiply powers at the same base, we just add the exponents. Negative 1/2 and 1 is positive 1/2. Excellent. And then, of course, if I multiply x minus 2 to the negative 1/2 times 1/2 x plus 1, I, of course, get 1/2 x plus 1 times x minus 2 to the negative 1/2. If you're saying, oh, well, how did you think to do this? Well, honestly, it's just a matter of trying to simplify my numerator as much as I can, especially because I have that negative exponent there, and it's kind of in my way. If I can factor it out, then I can move it to the denominator, which will make it a positive exponent, which is much easier to work with. So typically, if you've got, two terms and one of them's got a negative exponent in there, if you can factor something out so that you can move things around and have positive exponents, that is always a good choice. All right, so now I'm going to kick that down to the denominator, which is the whole reason I did this in the first place. And what I'm left with in the numerator is x minus 2 minus 1/2 x minus 1/2 all over x minus 2 times x minus 2 to the power of 1/2, positive 1/2. All right, simplify this a little bit further, and I get 1/2 x minus 5/2. That's 5/3, that's not correct at all. Minus 5/2 all over x minus 2 times x minus 2 to the 1/2. All right, draw a line, start off the next side. So, du dx. If I simplify this just a little bit more, I can actually pull a 1/2 out of my numerator, factor that out, and I get x minus 5. Whew. And see, right away, that feels good, because if you look at what we're aiming for, notice the x minus 5 in the numerator and our answer, that's a pretty good sign. That's a sign things might be going our way. And then in my denominator, I have x minus 2 and x minus 2 to the 1/2. Now, you might be like, hey, that looks nothing like the thing we're trying to get. Well, yeah, we're not done. We only found du dx. We want dy dx. So now we have to find our dy dx. Remember, dy dx is equal to dy du times du dx. We know our du dx, so let's do our dy du. Remember the derivative of the natural log of u. So remember we have y is equal to natural log of u. So dy du is equal to 1 over u. That one's nice and easy. Okay, so now we can get to our answer. Dy dx is equal to, well, dy du, which is 1 over u, times du dx, which is 1/2 x minus 5, all over x minus 2, x minus 2 to the 1/2. But I can sub out that u with what u actually represents, which, if we remember, is, sorry, I've forgotten what it is already, x plus 1 over the square root of x minus 2. Okay, doing a little bit of simplification magic, this becomes the square root of x minus 2 over x plus 1 times 1/2, or better yet, I'm just going to move that 2 to the denominator, x minus 5, 2 times x minus 2, and remember x minus 2 to the 1/2 is the same thing as square root of x minus 2. All right, then I can go ahead and cancel these guys out. They're gone. And what I'm left with is dy dx is equal to x minus 5 all over x 2 times x plus 1 times x minus 2. And hey, that's what we were looking for all along. Ta-da! Sweet. So sometimes you gotta play with it a little bit to get it in the form that they're looking for, but just play around with it. You'll find it. Next, we've got y is equal to log base 5 of t to the power 4 minus t to the power 2 plus 1. Okay, this isn't a natural logarithm anymore, so it's a little different, but the process is the same. First, we'll set our u, which is t to the power 4 minus t squared. And again, a lot of you will drop the step where you actually assign u, but it's really good practice because we're going to need it when we get to integrals. This means du dx is 4t cubed minus 2t. All right, so now we've got y is equal to log base 5 of u. And from our result that we got earlier, we know that dy dx of that is going to be 1 over u times du dx. Right? Because, oh, sorry, not 1 over u. That would be for natural logarithm. 1 over u natural log of 5. There we go. So it's 1 over u times the natural log of the base of our logarithm. All right, so now we just do some substitution. This means dy dx is equal to 1 over, okay, our u is t to the power 4 minus t squared plus 1 times the natural log of 5. I never give myself enough space. And then our du dx is just 4t cubed minus 2t, which means dy dx is going to be 4t cubed minus 2t all over the natural log of 5 times t to the power 4 minus t to the power 2 plus 1. Ta-da! All done. Alrighty. B. Y is equal to log base 10 of 2x minus 5 all to the power 3. So, same business here. Let u be equal to 2x minus 5 to the power of 3. Then du dx must be 2x minus 5 to the power of 2 times the derivative of the interior function, which is 2. Don't forget your chain rule. It's really common to kind of forget that step. Forget about that last 2 there. Don't forget about it. Do your chain rule properly. All right, so then we've got 6 times 2x minus 5 to the power of 2. All right, now what we've got is, I got to turn off my notifications. Sorry about that, folks. Apparently everyone wants to talk to me right now. I really don't want to restart this, so you're just going to have to put up with it. dy dx is going to then be equal to 1 over u natural log of 10 times du dx, which is 1 over 2x minus 5 to the power of 3 natural log of 10 times 6 2x minus 5 to the power of 2. Oh, hey, look at this convenience. Goodbye, and this becomes a 2. Right? So we can simplify that really nicely. And our final answer becomes 6 over natural log of 10 times 2x minus 5. I don't know why I left that as a 2. That should just be gone. There we go. That's dy dx. Okie dokie. Final example. Differentiate y is equal to x to the power of root x. Okay, so this one's a little weird because it's got an x both in the base and in the exponent, which makes it a little bit trickier. But you know, whenever I have that exponent with a variable in it, and I don't want it to be an exponent, we can use that trick we've used before. Let's take the natural log of each side. So we're just taking the natural log of both sides. Wow, I can't write today, or any day, in fairness. All right, so I take the natural log of both sides, and that allows me to rewrite this as the square root of x times natural log of x. So I've gotten that exponent out of the way here. Now I can take the derivative of both sides. So we're going to be using some implicit differentiation here, and we're going to have to do some product rule. So the derivative of ln y, well, that's just chain rule, so that's just going to be 1 over y times dy dx. Then the other side, I have to do some chain rule. No way around it. So I'll just, on the side here, quickly do our f prime, etc., ff prime, etc. So I've got f is our root x, f prime, or I'm actually going to write this as, just for convenience, x to the 1/2. That means f prime, I'm going to do this one real quick, 1/2 x to the negative 1/2. G is going to be natural log of x, and g prime is, of course, 1 over x. So we've got that on the side there. So let's do our product rule. Fingers crossed I left myself enough space. We'll find out. It's going to be an adventure for everyone. And move that over just a little bit to help with the, making that have enough space. Okie dokie. So I've got f prime, which is going to be 1/2 x to the negative 1/2, times my g, which is natural log of x. Hush, honey, I'm doing math. No, it's calculus time, not petting you time. Then it's going to be f, which is x to the 1/2, times our g prime, which is 1 over x. All right, now I have 1 over y times dy dx is equal to, so I can simplify this a little bit. I'm going to rewrite this one as ln x all over 2x to the 1/2 plus, sorry, my cat keeps stepping on my notes, plus, and then I have, remember, 1 over x is the same as x to the negative 1, so if I put those two together, what I'm going to get is 1 over x to the 1/2. So basically it's 1/2 minus 1, which is negative 1/2, which moves to my denominator. So now I have 1 over y times dy dx is the natural, I should get my common denominator here. That's going to be the natural log of x plus 2 all over 2x to the 1/2. All I did there was just found a common denominator by multiplying the top and bottom of this fraction by 2. All right, now that I've got that, I'm almost done. Last step is to get dy dx by itself, which just means multiplying y to the other side. And I get y times the natural log of x plus 2 all over 2 root x. Dunzo. My cat left, so good timing, cat. I was done. All right, so here we go. That's the end of that one. Everything is the same as everything we've done in derivatives up to this point in terms of, chain rule, product rule, quotient rule. The only difference is you have a few new types of derivatives to incorporate, like the natural log and exponential functions, but the process hasn't changed. I should go see what all of those notifications are for. I bet you anything it's you guys asking me questions. Bye.